So we know that a good, well-behaved wave function has to be normalized, but let's think about how we make sure that the wave function is normalized. So remember that normalization condition means that the wave function integrated, the complex constant times the wave function integrated over all space is equal to 1. So if it's not normalized, then there should be some factor, some constant that I can multiply my wave function by in order to make sure that it is normalized, that it is equal to 1. So in other words, if let's say that this summed up to equal 1/4, well, if I multiplied both sides by 4, then it would equal 1. Multiplying both sides by 4 is the same thing as multiplying both of my complex conjugate and my wave function itself by 2, and then that makes sure that that equals 1. So in this case, 2 is what we call the normalization factor, or normalization constant. So let's do an example of that and see how that works. So in this example, we're going to use the wave function psi is equal to sine of n pi x over a, where n and a are constants. And the domain of this function is 0 is less than or equal to x is less than or equal to a. So all space means that I'm going to integrate from 0 to a, all values of x. Now notice that this is not an imaginary wave function, so psi star is just equal to psi. So I'm going to take psi times psi, which gives me sine squared n pi x over a dx. And I want that to equal 1, but it's only going to equal 1 if there's some constant that multiplies the wave function. We'll call it n. And so psi times psi is n squared sine squared. And so what I'm going to do is I'm going to solve this integral and solve for n. So this is how I find that factor which ensures that this integral equals 1. Okay, so that means that 0, since n is a constant, n can come out of the integral. So 0, integrating 0 to a, sine squared n pi x over a dx is going to equal 1 over n squared. I just took all my constants over to the other side so I can focus on what is the value of this integral. So I can either try to figure out how to do this by parts or by substitution or something, but you know what? Let's just look it up in a table of integrals. So my table of indefinite integrals tells me that sine squared ax dx is equal to x over 2 minus sine of 2ax divided by 4a plus a constant. Okay, so when I'm looking up stuff in an integral table, they're always going to use a for any constants. So this is just any constant that shows up in my integral, right? This a is not the same as this a, right? So rather than saying a, because I already have a over here, let's change that variable to bx dx. So then this is x over 2 minus sine of 2bx over 4b, so that I don't get confused with the different a's. So now if I look at my integral, I can see that there's this n pi over a that is multiplying x, and in the integral table it says b. So I am going to equate b to n pi over a, Okay, so that means that the solution to this integral is x over 2 minus sine of 2b, but b is n pi over a times x, divided by 4a, or 4b, but b is n pi over a, so 4n pi divided by a. And then this whole thing, I don't need the c because I'm going to evaluate this from 0 to a, and that's going to give me my value of c. So that has to be equal to 1 over my normalization constant squared. Okay? So I'm going to plug a in for each x. So I have a over 2 minus, when I plug 0 in for x, that's a 0, so minus 0. Then I have minus, plug an a in for x, the a's cancel, and I have sine of 2n pi. Sine of any even number of pi is equal to 0. So that's going to be 0. When I plug a in here, I'm going to get 0. And when I plug 0 in here, sine of 0 is 0. And so this whole mess of sine stuff, when I plug in my unit, my limits, goes to 0. And so I end up with this is equal to 1 over n squared, or n squared is equal to 2 over a, or n is equal to the square root of 2 over a. And so my normalized wave function then is going to be equal to square root of 2 over a sine of n pi x over a. And that's my normalized wave function, where the normalization constant is this.